Good afternoon, everyone. I welcome, on behalf of ISRS, I welcome all of you in this special lecture on the occasion of World Environment Day. So today we have a very distinguished scientist with us, Dr. M. Rajivan. Rajivan sir will speak about the science of climate change. So now I request Secretary ISRS, Dr. Praveen Thakur, to initiate the session.
Thank you, Dr. Poonam. So it is our immense pleasure to welcome our distinguished lecturer for the World Environment Day, Dr. Rajivan. And we will also like to thank our president, Dr. Prakash Chauhan, who has initiated this communication with Dr. Rajivan, and he has gracefully agreed to our invitation to give his talk on this World Environment Day. So, although Dr. Rajivan does not need any formal introduction, for the sake of our ISRS members and other participants who have joined live in today's session, I will briefly read the profile of Dr. Rajivan. Dr. Rajivan is presently working as a distinguished scientist at the Ministry of Earth Science, and he has served as Secretary Ministry of Earth Science for 5.5 years from December 2015 to July 2021. And Dr. Rajivan, being born in a small village near Kanyakumari district in 1961, later on he pursued his physics from Madurai Kamaraj University and also completed his PhD in physics from University of Pune. And after his college education, he joined Tata Institute of Fundamental Research in Mumbai in 1983, and he joined Indian Meteorological Department as Class 1 officer after clearing the UPSC in 1986. After serving IMD for 23 years, he has also served as a senior scientist in Department of Space. And in February 2015, he was appointed as director of our prestigious Indian Institute of Tropical Meteorology under Ministry of Earth Science. And in December 2015, he was appointed as a secretary to Government of India, MOES. And after serving 5.5 years as secretary, he was superannuated from Government of India in July 21. And Dr. Rajivan is well known for his significant contributions in tropical meteorology research, and he has made significant contributions in the Indian monsoon variability, monsoon prediction, climate change, extreme weather events, mesoscale convective system, and satellite data applications. And he has developed many forecasting tools and data products which IMD is using for its operational use. And during his tenure as secretary, he has started many new initiatives, for example, for improving the weather and climate services in the country, especially for the prediction system. And also, he launched the prestigious projects like the Blue Economy Policy and also ambitious Deep Ocean Mission project of Government of India with more than 4,000 crores of budget. From the academic field, he has more than 140 research papers under his publication with H index of 51 and more than 11,500 citations. And he has supervised 10 PhD students from University of Pune, SP University, Tirupati, and Andhra University. And and Dr. Rajivan is also fellow of all the 3 science academies of India, namely Indian Academy of Science, Indian National Academy of Science, and National Academy of Sciences, India. And he is also member of International Academy of Astronautics, Paris. And he is member of this World Climate Research Program, Asian Monsoon Panel, senior level advisor on the Commission of Climatology. And currently, he is also expert member in research board of United Nations and World Meteorological Organization, Geneva. So with this, we formally welcome you, sir. And I also request our President ISRS, Dr. Prakash Chauhan, to welcome Dr. Rajivan.
Thank you, Dr. Praveen Thakur, Dr. M. Rajivan, all the members of Executive Council of Indian Society of Remote Sensing, and all the participants and esteemed members of the society. Good afternoon to you all. It's my pleasure to welcome a very eminent person today for this talk on World's Environment Day. Dr. Rajivan, as you have heard, has a great profile, and he is going to talk about the science of climate change, which is very apt on the occasion when this year's theme has been declared as the only one Earth, and all of us are aware that how the Earth is facing different challenges in terms of the climate variability, which is mostly caused due to the anthropogenic reasons. And I'm also happy to inform Dr. Rajivan about the society, that Indian Society of Remote Sensing is a very large professional society, sir. We have more than 5,800 members across all the countries, and the society operates in terms of local chapters across the country, and large amount of professional activities are being carried out by society, and it also has its international linkages with societies like Asian Society of Photogrammetry and Remote Sensing, as well as International Society of Photogrammetry and Remote Sensing. So I would like to extend my warm welcome to you, sir, and my appreciation and thanks for taking out your precious time to give us a overview about the science of climate change and how the climate change is going to affect our life, and what kind of climate action plans for mitigating these effects we should have. Thanks a lot, sir, and we all eagerly look forward for your talk. Thank you, sir.
Thank you very much, Dr. Prakash, and thank you for inviting me to give this talk in term for the ISRS Environment Day celebration. I'm very delighted to be a part of this function today. So I'll be giving about 45 minutes presentation on science of climate change, and I will share my slide. I think you are able to see this. Hopefully, you are able to see this. Okay. Yes. So I will be talking. I'll be talking about science of climate change for next 45 minutes, and as all of us know that Earth's climate system consists of these 5 spheres: atmosphere, hydrosphere, lithosphere, cryosphere, and biosphere. And all these spheres are interactive systems, and it also has feedback within the system as well as among the system. And the whole Earth system have these components, and these components really play an important role. Any changes in any of these components can have a serious impacts on other components also. So it's a close-knit kind of a climate system. And if you really understand, if you really try to understand more about that climate system, this cartoon will give you some more information. For example, anything of solar energy is our basic inputs, energy input coming from outside our system. And but then we have land, we have ocean, we have biosphere, we have cryosphere, we have rivers, we have human influence, human activities, and all these things. And the atmosphere, we have clouds, we have aerosols, and in some places we have volcanic activity, and clouds precipitate out, and the rain comes down, it flows through the rivers as well as in other places. And in the ocean, in the ocean, and we have ocean circulation, ocean interacts with the atmosphere, atmosphere influences ocean. It's a completely a kind of a close-knit kind of climate system which we have. And as I said, that any changes anywhere in any part of the system can have a serious implications on other components. And I will start with this radiative balance. I think you're all remote sensing people. I'm very sure that you are very familiar with this kind of diagram. As we know that our Earth system is radiatively, there's a radiative balance for the Earth system. Whatever solar radiation we get, the same energy is going out in terms of long-wave radiation. And so there's an equilibrium in terms of incoming solar radiation and outgoing long-wave radiation. And incoming radiation, there's not much changes are happening. If you see that for last many years, sun's radiation, of course, you have 11-year solar cycle, and also you have in many years 10,000 to 20,000 time scale. There may be small changes, especially in the rotation of the Earth, etc. But that may not really influence our Earth's climate system. But what it can influence climate system is what is the radiation going out. For example, if you have greenhouse gases which can trap the long-wave radiation which is going out from the system, it can retain the radiation more, and the Earth will be getting more energy than what is more than the equilibrium, and more energy means more warming of the Earth's planet. And that's what exactly we are worried about it because of the human activities, the concentration of greenhouse gases. Greenhouse gases are nothing but it allows the solar radiation to pass through it, but doesn't allow the long radiation to go out. And so the most important greenhouse gas is carbon dioxide. That's mainly contributed by human activities like industries, transportation, deforestation, etc., and land use changes, etc. And also we have methane, we have ozone, especially surface ozone, and also other small gases like nitrous oxide, etc. So put together, all greenhouse gases can really trap the outgoing long wave radiation, and it can give more energy to the system, and thus leading to the so-called global warming. And these are all increase in greenhouse gases. Water vapor is a very important greenhouse gas, but it's a natural gas. It doesn't change. It is conserved. And but what we are worried about is carbon dioxide, methane, ozone, nitrous oxide, etc. And what are the human activities which can contribute is basically industrialization, deforestation, public transport, and land use changes. And for any studies related to climate system, we need observations because both ocean as well as the atmosphere as well as cryosphere, we need huge observation platform, huge network we need. And WMO with all other UN agencies put together has come out with a global climate observing system called GCOS. I'm very sure that at least some of you in the remote sensing community will know about this GCOS, and basically to ensure the availability of global observations for climate studies. And it's a long-term observation studies are available with this, and we have long-term data from all different components of the Earth's climate system. And in this GCOS, the most important thing I will tell is the Earth observational system, satellites. It's a UOS. And we have plenty of satellites because you are remote sensing people. I thought I will share this slide. And so in addition to typical AWS and surface observatories or radio sound observations, satellites provide a lot of information, very useful information. And also the satellite advantage is it can cover large area, and also you can have repeated observations, and you can have a continued observation, like geostationary satellites can give you continuous observations, etc. So satellites will provide, satellites are providing us very valuable information in understanding our climate system and to monitor how the climate system is changing. And the most important, the climate observation network is the homogeneity. We need to really have a consistent observation. Observation taken by satellite on a parameter should be also the same value should be taken, should be also for example, the automatic weather stations. So the consistency among all these observations are very important. There are ways to make this observation very consistent and reduce the errors, etc. And so this global observation networks is a very important component. And these are the changes which we have seen in the past in carbon dioxide, methane, etc. So this is so-called Paleoclimate Data. And you can see that carbon dioxide for many years, in thousands of years before 1850, you can see that there are changes happening in the earlier, but carbon dioxide concentration never crossed 300 ppm. Now it has gone substantially, it has gone up, and especially after 1950s or 60s or so, after the industry revolution happened. And this is now carbon dioxide concentration, latest one I understand is around 420.19 or so, 420.19. So it's unprecedented kind of observations, which the value which we have now at carbon dioxide. And methane also has a larger value, a very large rise. And bottom one is the temperature. And I will give a lot of credit to the Charles David Keeling. We all should really appreciate his vision. He started this Mauna Loa Observatory in Hawaii. He started this carbon dioxide observations, very, very authentic and very valuable, and also very precise, very big quality, high quality observations of carbon dioxide. He started in 1950s. for many years, he himself was taking observations. He was responsible for continuing these observations. Now I understand it was taken the observatory was taken over by NOAA now, but he is still held responsible for maintaining the observational values. And December 2021, it was 416.71 ppm. Now April 22, it 420.23. So that's the latest value which we have. And if you can see that large increase in the carbon dioxide concentration below 320 to us, and now it is almost 420 plus value. And you can see that small red line, if you can see that, that's is going up and down. That's basically a kind of a seasonal variation because of the changes in the vegetation. And so in the atmosphere aerosols also plays a very important role in addition to greenhouse gases, even though the short-lived component, unless greenhouse gases which have a lifetime of about 60 years or so, and whereas aerosols, the short-lived lifespan is about 1 week or so. And so we have also, thanks to ISRO and IMD observations, we have a good network of aerosol observations for many years, at least from 1985. And this is one result which I have taken from paper by ISRO scientists, which clearly shows the increase in the aerosol content in the atmosphere for since 1985. So aerosol plays an important role. It basically has a cooling effect on climate, unless it is a black carbon aerosol, it has a warming effect. Otherwise, sulfate aerosol, which is very important component of its climate system, has a cooling effect. And also we make changes in land use in terms of agriculture. First of all, agricultural land has expanded. And also the way we do the agriculture also has changed a lot, and the cropping pattern has changed a lot. And these observations are again taken from kind of proxy as well as satellite observations, which very clearly shows that the cropping pattern or land use changes happen. And these land use changes also can impact our climate because mainly through land surface albedo. Albedo is nothing but a reflection of solar radiation. So if, for example, a grassland is removed and the soil is exposed, the albedo can change, etc. So, and also soil moisture will play an important role. So land use changes are also a very important component of our climate system. Now I will talk about what we have seen from last 100 years of observations and what these climate models are projecting about our future climate. And so question is how we predict, we know from observations, we know how the climate has changed. We have plenty of data and we can really see how the climate has changed. The question is how we know what will happen in our future climate. And normally we do with this kind of project, and we don't say it's a prediction. The climate change studies, future projections, we call it a projection. It's not a prediction because projection has a lot of that kind of exercise. We have a lot of uncertainty. So we don't say future climate prediction, but we say future climate projections. And so we make use of coupled climate or system models in making projections for future climate by assuming certain scenarios of greenhouse emissions. The scenarios of greenhouse emissions means, for example, whether we'll have a kind of a scenario in which the present scenario will continue, the present rate of greenhouse emissions will continue, or whether we will put more restrictions on greenhouse emissions, for example, cutting down fossil fuels and going into alternate energy, and whether we'll have a business as usual scenario. So these are the future greenhouse emission scenarios. It's all done by IPCC. They have at present I think that they have 4 different scenarios, and depending upon strict actions, if you take, the greenhouse emissions can be controlled, and if you don't do anything, it will simply go as it is, and that's a different scenario. So we should know the different kind of greenhouse emission scenario. And model generally, this Earth system model generally treat all the components of that system, which I have shown a figure in which all the different components are shown. All these components are treated in the Earth system model. And present day models, thankful for some, if you may be knowing the IPCC 6th report has come out. And if you really see, based on so-called CMIP6 models, and if you really see the earlier version, fifth version of the models and 6th version of the models have improved substantially in many components. And so the present day models have improved in fidelity as well as also resolution has changed because resolution has improved because we have now more and more computing facilities. And but we should tell that model precisions always have uncertainties. And these are the basic equations, which is all the same as a numerical weather prediction, which we use it for next short range for 3 to 4 days, etc. The physics and maths are same. Only thing is we run it. Resolution of the model is different. Normally climate models are coarse resolution, and for short range forecast we use only atmosphere, whereas when we go for climate we need all the components like atmosphere, ocean, cryosphere, biosphere, etc. And this is the physical process which are very important for weather prediction. So the same kind of physical process when we call parameterization of a physical process in the model, physics component. This very tough proposition, and we use this kind of parameterization methods in weather prediction as well as in the climate models. And we need a huge computer. For example, India's Pratyush computer, which is available in IITM, is one of the supercomputer which we can use for making climate change projections. And we have developed last 7, 8 years, 5, 6 years. We have developed. We means IITM scientists have developed a system model, India's first system model. We should be very happy. We should congratulate the team. And so this model is now second version also is available. And this model has for the first time it participated in the IPCC climate change projections exercise, which was done by IPCC. And this model is pretty good, and it gives kind of a good, these are some of the verifications of the model with the different observation, like for example, CA is improved, and for example, top of atmosphere fluxes, you can see that it is captured very well. And temperature is stabilized at about 14 degree global temperature. Maybe I don't know how many of you know that global temperature, if you average the whole globe, our temperature will be about 14 degree or so. And SST is also, and top of atmosphere, the flux is, the net flux is almost close to 0. That means there's a big balance of incoming as well as incoming solar radiation and outgoing long wave radiation. So it is within 1 parts per meter square. So the model is pretty good. This model is being used by IITM scientists, Center for Climate Change Research in IITM, are making use of these models for different climate change runs as well as climate change scenarios and understanding climate, etc. And we have brought, when I was secretary, we have brought this beautiful assessment of climate change over the Indian region report. This is the first time that India has come out with a national climate change assessment. And we normally believe in IPCC reports and we're very happy with whatever they say. And so I'm not questioning the IPCC reports, but the IPCC report, normally if you see that it doesn't have details about what is happening in India, and also what is going to happen in India. So we thought that we will make a separate assessment report, and with Dr. Krishna has led this team at IITM. And this report is the highlight of this report is it's free of cost. We paid money to print this. We in Share Science paid money to print this report. I wanted the report to be an open access book, and people should not pay money to understand what is happening in the country. So it can be easily downloaded. It's just search Google and you can download this book free of cost. And already it is 155 citations and 242,000 downloads. And so if you really talk about climate change, and so if we know that global warming is happening because of the imbalance between incoming solar radiation and outgoing long wave radiation. And if the temperature, if the global warming happens, the mean is shifting. The mean is shifted towards right, and so there's a warming. If you assume that it's all temperature, everything is a kind of a normal distribution. Left hand side, the top one shows that if you shift towards right, what is happening is also the extremes are getting more. So you have tendency of getting a probability of getting extremes or more. Or assume that mean is same. just to increase the variability. That's the bottom, middle one. Left-hand side, middle one, which clearly says that you don't change the mean, but increase the variability. That also will contribute to more probability for extremes. But if you have both mean as well as variability, you can definitely will have changes in the extremes. So what is happening with the global warming? You get more probabilities for extreme weather events like heat waves, extreme temperature, extreme precipitation, etc., which I will explain little later. And if you really see the latest IPCC climate change assessment report, this is a global perspective. I'm not talking about Indian perspective. It's a global perspective. How much we so and see, as I told that the models have uncertainty, so we can attribute kind of a likely, very likely, extreme likely, virtually certain kind of attributes to these kind of projections, depending upon how robust these observations are. And so we can put this kind of table. You're saying left the y-axis is basically confidence in projected changes of global warming level of 2 degrees or so. And x-axis shows confidence in attribution of trends to human-induced climate change. The basic question of climate change is, we are not talking about human activities, and we know that human activities is causing climate change. Now, question is whether all climate change components can be attributed to human activities. In our observations, what we are seeing, how much we can contribute to human-induced climate change. We have a tendency of attributing any abnormal things to climate change. For example, heavy precipitation somewhere in Ahmedabad. Immediately people come out and say, oh, it's a climate change. It need not be. It could be natural variability. So there are studies of we call attribution studies. Of any event, we should be able to tell that whether it can be natural variability or it can be a human-induced climate change. So this table very clearly shows that, and you can say L likely, very likely. You can see the top one. You can see that for confidence in projected climate change is virtually certain, and also it's extremely likely that these changes are happening due to human-induced activities. There is two parameters. One is heat days or heat waves, and also cold nights and days. These two things, cold heat days and nights, and heat waves and cold days and nights, are projected changes. It's very, very virtually it is certain changes, and it is all extremely likely because of the human activities. Other climate indices are not very likely contributed by human-induced activities, except for example, a tropical cyclone. Sorry, heavy precipitation. Remaining like tropical cyclones and agriculture and ecological droughts, compound dry and hot events are not very likely. The belief is, the trust is that only medium confidence we have about its influence by human activities. But heat waves and cold days and cold nights have very large confidence that these are all contributed by human activities. And these are the surface air temperature trends. So if you take last 115 years of data, so everywhere it is warming. Gray area is area where we don't have adequate data. And in the Greenland, there is a small cooling. Otherwise, everywhere it's all warming. And warming is not uniform. You can see some areas you warm more, some areas warming less. And you can see the Arctic region warming is very high. Higher compared to other places, and we call it is Arctic amplification of Arctic warming, and that can have a serious implication in terms of melting of sea ice, etc. And if you really take global average and plot a graph from 1850 to 2020 or so, this looks like this, and global mean temperature is changing, and it's all contributed by annual hottest temperature as well as annual coldest temperatures. And you can see the trend in annual coldest temperature is much more than annual hottest temperature. So the night temperatures are warming up very fast when compared to the daytime temperatures. And land temperature is more warming much more faster than ocean temperature. These are the important inferences which we can get it from this figure. And there are many changes are happening in other components of surface, climate system, which, for example, sea level rise is increasing. If you take an observation from 1993, and right-hand side top is ocean heat content. So that also is increasing. That means because of the global warming, not only the sea surface is warming up, but the whole ocean depth also, maybe about 150 to 200 meter ocean heat content also is increasing. Other important activity, important climate system changes is happening in ocean acidification, because ocean is a good sink. It can absorb carbon dioxide. So more and more carbon dioxide is absorbed, then its pH value will change, and it will become more acidic. And there are observations which very clearly show that ocean acidification is happening, and it can have a serious implication in terms of its ocean biodiversity, marine life, etc. And this is an important diagram which I normally show to people whenever I talk about climate change. This very, of course, this little bit old figure, but it gives a good message. The black line, I'm very sure that we are able to see very well. The black line shows the observations of temperature changes. And the question is how much this observation, if you see the last few years, you can see the beautiful rise, temperature rise, sharp rise in temperature. The question is whether it is natural variability, part of natural variability, or it is influenced by both natural as well as anthropogenic. So what people have done is they run a model without changes in the carbon dioxide or greenhouse gases, and then they try to understand what these observations show as temperature. So the green lines are observations of temperature changes, especially last few years. You can see that it is much less than what we have seen in the observations. And when we put these changes in the greenhouse gases in the model and then try to simulate this kind of temperature changes, it very much, the red line, you can see that it very much matches with the observations, which very clearly shows that last few years of last decades, 4 or 5 decades of temperature rise, sharp rise, is mainly contributed by anthropogenic activities or human activities. There's no doubt about it. And IPCC has very categorically written that kind of sentences saying that human activity is causing the global warming. And if you really see these future changes in temperature, you can see that there are, as I said, that there can be different kinds of scenarios, simulated changes at 1.5 degree, which we really want, and which may not happen. And middle is simulated changes about 2 degree warming and simulated changes at 4 degree warming. So at least 2 degree warming is expected. You can see that the whole globe is warming, and you can see the northern part of the whole globe is Arctic. Arctic is warming much more than any other region. It will have serious implication in our climate system. India, so we have, these are the observations which we have from IMD observations. We have about 350 observations or so, temperature observation, and which very clearly shows the last few years. Here also warming is happening in India. You can see the spatial distribution. Everywhere it is warming except a few places in Rajasthan or few places in Uttar Pradesh, Bihar, etc. Otherwise, everywhere the warming is happening. And warming trend is also very similar, 0.62 per 100 years. This is also similar to the global warming. And if you really see how much models are projecting for future climate change, this is the figure. And I request you to see the middle one. Top one is for the middle one. Top one is showing 2041 to 2070. Bottom one is for 2070 to 2099. So we say near future climate and far future climate, and you can see that there's a warming everywhere, and especially northwestern parts of India, warming is happening more. And this is the time series. You can see that different scenario: RCP 226, RCP 45. RCP 8.5, and out of this, I think I such that you believe in more in RCP 4.5, which is a reasonable scenario. You can see that temperature rise you can expect for about 2.5 degree or so by 2100. And you can see the big spread. That is basically uncertainty in the model. And if you really see how the cold nights and cold days as well as warm nights and warm days will change in the future, These are very beautiful projections which IITM people have brought out. Is cold nights are going to reduce, and cold days also going to reduce, whereas warm nights and warm days are going to increase. So night temperatures will be much cooler and much warmer now, and whereas warm nights and warm days are increasing. That means daytime temperatures will be much more than what we have now. And of course, there is a lot of uncertainty. If we really see the 4.5 scenario, exceedance rate, for example, warm nights is more than 50. And I will talk about now next few minutes about heat wave, because this year we had a very severe heat wave events over the country and also adjoining Pakistan. In 2003, there is a severe heat wave occurred over Central Europe. It's a very famous heat wave, and about 40,000 people died. And in a developed countries like France and Germany, people died. And the climate modeling studies suggested that this heat wave could be a part of increasing global warming caused by human activities. The attribution study was made, and they categorically told this 2003 heat wave sure it happened because of the human activities. It cannot be explained by natural variability alone. And so these are the future climate, future heat waves which are projected by climate change models. And you see the bottom two models with 1.5 degree warming and models with 2 degree warming. You can see that most of the tropics, we will have more heat waves, and the change is significant, and also its change is robust, including India. And you can say between 1.5 and 2 degrees, big changes are happening in India as well as in countries like Africa and northern parts of South America, etc. So in future, this warming is increase in heat wave is very much imminent, and it will happen. And not only in terms of frequency, but in terms of its intensity and also in terms of its duration. So once the heat wave starts, it is likely to prolong for a longer days now. Indian heat wave is one of my students have done for their PhD, and this is the mean heat wave left hand side. You can see that top one is the heat wave frequency left hand side, and left hand side bottom is the heat wave duration. And right hand side, the same figure, it clearly shows how the climate model is able to predict, it's basically a simulation of this frequency as well as duration. The model is pretty good in making this prediction. But if you see the right hand side, and you can see that there's a significant trend is happening in terms of frequency, in terms of duration, or also the maximum duration of the heat wave event. And future change, what will happen in India about future climate, heat waves. And from the National Climate Change Assessment Report, we can see that frequency is going to increase in future, and also the heat wave duration, both the frequency as well as the duration will change. And this is a very interesting result. So when we assume that there are changes going to happen in future, what will happen to how many people will be exposed to this kind of heat wave stress and heat wave impacts? And you can see the top one, the India map, India-Pakistan map with 4.5. You can see that especially over the Indo-Gangetic plains, the more people will be exposed, and it's almost 1.25 million people per event will be exposed. And the bottom one also shows the same thing. You can see that almost 389 million people will be exposed in the future climate change. So more and more people will be exposed, especially in the northern parts of the country. And this is the 2022 Indo-Pakistan heat wave. So it's not like Indo-Pakistan cricket match. It's here we have good harmony in the heat wave between India and Pakistan. And this is the paper, a report came out very recently by Mariam Zakaria et al. It has become very famous. It has come in newspaper, etc. So I taken from this report, and you can see the left-hand side. It shows the March-April trends and daily maximum temperature. And left-hand side is from a data set called CPC, and right-hand side is from IMD data. Both are showing that Northwest India is warming up. and which is also known very well. The most of northwestern parts of India is warming up. And trends are significant, especially March, April is warming up. This is the data, this is the land surface temperature data, which I thought I will share with remote sensing people. It is taken from Copernicus Sentinel-3 mission data. It's available on the website. It's online, it's available. These are all surface temperature. See, IMD and any observatory weather observatory, they measure surface temperature at so-called Stephenson screen. It's at 1.2 meter above the surface Earth surface. Whereas this is so there that so the temperature at the Stephenson screen is normally below. Normally it's a smaller value when compared to the land surface. Land surface Earth skin data is much more. And this is the skin data because it measures the land surface and the satellite, and it's a 29th April 2022 at 10:30 a.m. You can see the temperature even crossing 3 over northwest India. This data will not be, this kind of observation will not be reported by IMD observation because at 1.2 meter, these values will not be there. It will be much reduced, not much reduced, but it will be smaller than this land surface temperature data. This is the heat wave which occurred on 29th April. Of course, it was a prolonged heat wave. And this is also by the same paper by Mariam Zakaria. What is the same thing, left-hand side is actual data, 40, crossing up to 40. This is a maximum temperature for monthly average, March and April together. And right-hand side shows the anomalies even crossing up to 5 degrees or so. And this study has very clearly brought, this study also is a kind of an attribution study, and it has become very popular recently. And this study has very clearly told that because of the climate change, the probability of an event such that happened in 2022 has increased by a factor of about 30. And so probability has increased by about a factor of 30. It's very, very important message which we normally don't want to listen. But this is the fact that heat wave, probability of heat waves is increasing very high. And so I try to understand, of course, the very, very preliminary results, try to understand what really happened. So, of course, it's a very, very preliminary results, but I want to share some few observations. Probably, I'm very sure that some of you will be inspired to do very detailed study about this heat wave. And so the past studies of study like Ratnam or Rohini et al. 2016 very clearly categorically told that the heat wave occurring in India is not a regional phenomenon. It's related to the global aspects. A large scale pattern is involved. For example, large scale Rossby wave. This is a Rossby wave pattern. This is a 200 hectopascal geopotential height anomaly from 1st April to 20th April, which very clearly shows a low, then high, a low, then high, which clearly shows a kind of a Rossby wave pattern over the middle latitudes. And these two papers, Ratnam and Rohini et al., have very clearly told that Indian heat waves are influenced by this kind of large-scale dynamical patterns, and especially Rossby wave patterns. And another three important parameters. So there's a dynamical forcing, but it also will be supported by local conditions, like what is the condition of soil. And soil, especially soil moisture. A dry soil moisture can give kind of a more sensible heat flux, and it can give feedback to the intensification of heat waves. That's what exactly happened this year. The left-hand side shows the OLR anomalies during the same period. You can see most of North India as well as Pakistan has a positive OLR, which means there was not much rains. And right-hand side shows the soil moisture anomaly, and which also shows the large depletion of soil moisture. Soil was very dry. And bottom one shows the vertical velocity, nothing but omega is positive there. Positive means it's basically sinking motion. So air it is at 500 millibar. So air is sinking over the Indian subcontinent, and which also gives so-called we call subsidence. Subsidence normally give rise to more temperature at the surface because adiabatic compression happens. And so depleted soil moisture, sinking motion, and it is influenced by large-scale Rossby wave pattern. Where everything put together, I think we had a very severe heat wave. And I'll move on to oceans now. Ocean also warming, and it's a paper. It's also again from the same report. Sarosik, for example, has written a chapter on this paper, and it clearly shows the Indian Ocean also is very warming, very substantially. Now a new concept has come about the heat waves over land. Also, there are heat waves over the ocean. We call it marine heat waves, and it's a relatively new area of research now. It's a first paper, I think, 2018 happened. It's published in Nature, which very clearly shows left-hand side. You can see that mean heat wave, marine heat wave frequency, marine heat wave intensity, marine heat wave duration, etc. And there are a lot of changes happening in the frequency. And if you really see the time series, you can see the total number of marine heat wave days globally. And you can see the black line is global average, and red line is if you exclude ENSO, what is so both shows an increase in annual marine heat wave days. And the marine heat wave is defined in terms of kind of a very objective criteria. For example, a threshold crossing 90% of present day, etc. at a given grid point. And a very objective criteria they used, and they found that marine heat wave frequency is increasing. And from 1925 to 2060, about global average marine heat wave frequency and duration increased by 34 and 17% respectively, resulting in a 54% increase in annual marine heat wave days globally. It's a very substantial improvement, such a substantial increase. And this is another paper also, it's very recent paper, again in Nature, is Alex and Gupta et al., which very clearly shows that left-hand side top one shows the maximum experience category. They have different heat waves, they made it in different categories like moderate, strong, severe, extreme, etc. You can see that most of the category are either strong or severe or extreme. And right-hand side shows the year of highest category. Also, you can see that recent year she is showing a highest category. And left-hand side, bottom left-hand side shows the maximum experience is surface temperature anomaly, also showing very large anomalies of 4 to 5 degree or so. Ocean 4 to 5 degree anomaly is very high. Land you can expect 4 to 5, but in ocean 4 to 5 degree anomaly is very, very high. And bottom, the rightmost, you can see that seasonality of most intense marine heat wave. Northern hemisphere, it peaks up somewhere in May, June, July, whereas in southern hemisphere, just reverse. And this is the Indian heat wave. This is again by Roxy's group, Saranya et al., 2022 to happen. And this also very clearly shows they have focused more on Indian Ocean, so that the results are almost same. So there are changes in the frequency as well as duration of marine heat waves over the Indian region. So this marine heat wave have serious implication in terms of marine life, marine biodiversity, marine life, as well as the whole marine ecosystem. This again shows the same thing. Now I'll move on to maybe another 10 minutes or so. I'll try to complete it. This is a trends of rainfall. It's a monsoon rainfall time series, which really clearly shows that there are year-to-year variation, but there's not much a long-term trend. So monsoon is a very robust system. But there are changes regionally. If you see the left-hand side, you can see there are trends happening, reduction in rainfall happening, especially Kerala, some parts of Maharashtra, some UP, Bihar, etc., and Chhattisgarh, etc. In the October, November, December, northeast monsoon, Tamil Nadu and all getting more and more rainfall now. This is how the model projections are for future. The good news is that most of the climate models are showing that our monsoon will be robust in next few years because of climate change, and nothing abnormal will happen in terms of seasonal rainfall. We'll still have good monsoons. We'll have plenty of rains, and so some models are showing a small increase, but we should assume that there's not much changes happening in the seasonal rainfall. And but as I told that climate change also can make changes in the variability. So we can expect more and more droughts to happen, more and more floods to happen. So this is a study made by our group a few years back to understand how the trends in droughts using a index called SPEI, standardized precipitation and evapotranspiration index. So it takes care of both precipitation as well as evaporation to calculate this index, and very clearly shows that and droughts can sustain for 6 months, 18 months, 12 months, 18 months, 24 months. So you can see that droughts in different time scales, it's showing a increase in terms of percentage area affected by droughts. And future changes, RCP 4.5 very clearly shows that frequency of moderate and severe droughts is going to increase in future. This is a heavy rainfall event. This is the left-hand side shows that anything between 10 and 15 centimeter, and right-hand side shows anything more than 15 centimeter per day, and which very clearly shows that these are the area where we should expect more and more heavy rainfall. And if you really see the, if you take the central India and take a kind of a time series and plot it, and you can see very clearly see that recent few years and the trends very clearly shows that the heavy rainfall events are increasing in terms of frequency. And rainstorm is nothing but you have an objective criteria to identify rainstorm. The heavy rainfall is normally caused by synoptic system, weather systems like lows and depressions forming any other system. So we have tried to understand how identify whether a rainstorm using a objective criteria, and then we try to find out how many rainstorms in a season and also how many rainstorm days. Assume that it will persist for 3-4 days, etc. And so then both the shows, both rainstorm events as well as rainstorm days are increasing. That means the not only heavy rainfall, increase in heavy rainfall is basically contributed by the increase in the rainstorms, which are contributing to heavy rainfall. And future changes, if you see that most of the heavy rainfall indices very clearly shows an increase in the future. So even though monsoon rainfall will be almost same, seasonal rainfall, annual rainfall, but within the season, there could be a lot of heavy rainfall events, increase in heavy rainfall frequency in this within the season. And this is again maximum 5-day precipitation or consecutive dry days. So heavy rainfall is increasing. Another important event aspect which we should remember is a consecutive dry days. In monsoon season, you know, you may not get 122 or 100 days every day rain. You get some rains, then followed by a dry spell, then again some rains. So what is going to happen in future is the dry spell, when it starts, it is going to prolong for a longer time. So consecutive dry days are going to increase in the future. And so that will have serious implication in terms of for agriculture. And of course for water resources. I will come to the last aspect is the tropical cyclone, which is also very important. I know that this is a very important two papers, Clinton et al. 2020, very authentic paper, and people who are very interested in tropical cyclone research, I think they should read this paper. So it came in BAMS. So this paper very clearly shows this study. This is a global study. The top one, I'll just describe the top one, right-hand side, the vertical bars. And you can see that which very clearly shows that the frequency, this is the top one is the percentage change in terms of number. The number is not changing. That means in future climate, the tropical cyclone frequency may not change. But bottom one of the same thing figure shows the very intense tropical cyclone frequency is changing, and little bit it is increasing, especially the northern Indian Ocean and also Northeast Pacific, etc. There is a change in the frequency of a very severe cyclone. And these two are very important. The tropical cyclone, right-hand side, again, you can just concentrate on right-hand side, very clearly shows that tropical cyclone intensity change projections are very clearly suggesting that whole globe, all global basins, global basins of tropical cyclones, the percentage change in the intensity change is going to increase. In North India, for example, about 4 to 5% changes we can expect. That means when cyclone forms, its intensity is going to be much more than what we have now present. And another important the bottom one right-hand side, bottom one shows how much percentage change in terms of tropical cyclone precipitation change. The rainfall associated with the tropical cyclone, that also is going to increase. And now for the North Indian Ocean, it is North Indian Ocean tropical cyclone, it's about 15 to 20%. That means in the future, global the warming climate, what will happen means the frequency may be same, but it will increase. It will once a cyclone form, it will intensify. Probability of intensification is very high, and it will have more. It will precipitate more. It will have more and more rainfall activity. And so this is also again some kind of conclusion from the same kind of people. Is the warming of the surface ocean from human-induced climate change is likely to fueling more powerful tropical cyclone. That's the message. Powerful intensity is very high. Tropical cyclone precipitation rates are projected to increase due to enhanced moisture associated with the warming. And proportion of severe tropical cyclone 3 and 5 has increased already. But in the future climate, 4 and 5 also is projected to increase. Most models says total number of tropical cyclone to remain same. Some regions will experience an increase in rapid intensification. How quickly it intensified. And in especially Arabian Sea, recent years, Arabian Sea cyclones is a gray area of research, is the tropical cyclones are intensifying much faster. Once it will become a low, then next day it will be depression, and next few hours depression. So the intensity, the rate of intensification is much faster now, especially over Arabian Sea now. And also a poleward migration of the latitude of maximum intensity. Also, see the whole belt is moving now north, and also a slowly moving forward motion of tropical cyclone. When it forms, when it moves very slowly. It's very dangerous because it has more lifetime over the ocean, so it's the probability of intensification becomes much more. So the ocean will feed a lot of energy to the cyclone, and so because it's a lifetime, the ocean is going to increase. And Himalayas, as last 1 or 2 slides, Himalaya is very important. The Himalaya, the rainfall, this is the basically temperature anomaly. You can see that the warming is not only over the plains, it is happening over the Himalayas also. And frankly speaking, Himalayan data also very clearly shows that warming is happening in the Himalayas. And also precipitation changes, this is also from the same report. You can see that rainfall is increasing, especially in Hind Kush area. And so also glaciers. Glaciers is very important. Remote sensing people know about glaciers. And last year, the Chamoli incident also was related to some extent related to glacier. And I am very sure that IARS and Darado has done a lot of studies. Dr. Prakash and group has done a lot of studies, quick studies, to understand what Chamoli incident happened. And we also, MOE's ministry also set up an observatory in somewhere in Himalayas. And now glacial area loss is in different regions, Himalaya from 60 to 2000. And there are changes happening in the glacier areas. So these are also very important area where we need to more observations, and remote sensing will play an important role of understanding glaciers and its dynamics, etc. So what is sure for next 30, 40 years? I'll summarize the whole thing. What I told is surface air temperature is going to increase in heat waves, increase in extreme weather like heavy rains, strong winds, intense precipitation, tropical cyclones, convective storms like thunderstorms. No change in mean monsoon rainfall, an increase in variability of monsoon, more floods and droughts, an increase in sea level as well as coastal erosion, which I have not touched upon here in this presentation. And these are all climate tipping point. It's a very famous paper. Already climate has changed and it's going to, the situation is very critical now. And already they have identified, climate scientists have identified tipping points. Nothing but tipping points are nothing but points of no return. For example, Greenland ice sheet, Arctic sea ice, a reduction in the area, Atlantic circulation slowing down into Atlantic circulation, Amazon rainforest, boreal rainforest in northern parts of US, West Antarctica ice sheet, coral reefs in Australia, Wilkes Basin in East Antarctica ice loss, and permafrost thawing. These are all very known indices which we have already documented that these are all tipping point. For example, the Arctic sea ice is melting. By 2050, September is the month where the melting is highest. So we'll have in 2050, we'll have an Arctic sea without any ice. Ice-free sea we can see in 2050. And that is though, it is not going to come back. So it's all point of no return. So these are all some critical points identified climate scientists. And this is the last slide. World Economic Forum has identified some of the top 10 risks over the next 10 years. And you can see that they are not identified any economic aspects or any political points to as climate risk. For example, wars between two countries, etc. What they put in the top 5, you can see that extreme weather, climate action failure, which is also very important. We don't take action, we just keep quiet. Natural disaster, biodiversity loss, and human-made environment disaster. These are all environmental issues. So World Economic Forum, which they are supposed to talk about business and economy, and they put environment in the top. And they say these are the 5 top climate risks in the world for next 10 years. With this, I'll stop here. And once again, thank you, Dr. Prakash and ISRS for giving me this opportunity to talk to you and interact with you. Thank you.
Thank you very much, sir, for this wonderful talk and taking us through the entire process of climate variability, starting from radiative transfer, and then how the excess amount of greenhouse gases are causing, the effects on various ecosystems. And of course, the work which has been done in India in terms of bringing out and documenting the effects of climate variability on various ecosystems is also widely appreciated. And you showcase that how the heat waves, which have been basically increasing, and this year was no exception. In fact, it is supposed to be the largest heat wave conditions during March and April period, which is also having its consequences on various ecosystems, including the reduction in crop yields. It's really been a wonderful talk, sir. And in that context, I would like to just mention that recently we also did at NRSC and IARS on work how this excess heat during March and April has affected the snow and the glacial systems. And to our surprise, large amount of increase in the snow melt rate and the discharge in the northern Himalayan rivers have been observed during this period compared to the last year anomalous data sets. So once again, sir, I would like to thank you for giving this wonderful talk. And I'm sure there must be some questions. So I will request Dr. Poonam to moderate the question and answer session.
I'm happy to see Dr. Sailesh Naik Saab is there.
Yes, sir.
Good afternoon,
Hey,
sir.
all
Good
of
afternoon,
sir. And Dr. Naik, sir. And you can switch on your camera, sir.
Yeah, I have to be there, Rajiv, and just to get myself updated what is happening around. Yeah, so it was a good talk. I think really enjoyed it, Rajiv. And thank you very much. Yeah.
Thank you, sir. So, Praveen, I think we can take up the Q&A session before we wrap up.
Yes. Sir, you can unshare your slides so that we are in the participant mode.
Okay.
Poonam madam, you can start after that, start the questions.
Yes, sir. Thank you, sir, for such a wonderful talk. So we have received a few questions from students as well as from EC members and all the ISRS members. So I will tell one by one. So the first question is, how can a balance be maintained between development and sustainability of the environment?
Well, whenever we talk about development, there is a need for sustainability. And that's a message now all countries are coming out. And
Yes.
Without sustainability, you cannot do development, because that will definitely impact on environment. So we call sustainable development. That's the key for all the governments, which UN is, for example, is sending the message. So they have developed 17 indices for sustainable development goals, and they are asking all countries to follow those goals. And for example, India, Niti Aayog is following a kind of a protocol to understand how many states are implementing these SDGs, so-called development goals, very strictly, and they rank also different states. So sustainability is key, and without sustainability, we cannot really do any development. We should not do any development.
Thank you, sir. Sir, there's one more question, that India has scored lowest among 180 countries in the 2022 Environmental Performance Index released recently, which is based on many indicators such as climate change, which includes climate change also. So, sir, can you enlighten us on this?
Well, I don't want to comment more, but I don't know the details, how this 180 rank has come, what are these parameters and all. And so, frankly speaking, I will not be able to comment that question.
Okay, sir. Sir, in the view of the recent heat wave that we all are experiencing throughout the country and throughout the subcontinent, sir, is there any way that these kind of heat waves or extreme events can be predicted so that the on-ground interventions can be made and we can save a lot of lives?
Heat waves can be predicted. Thankfully, we have good prediction system now in at MOES, and IMD does heat wave prediction, and at least 4 to 5 days before, at least sometimes even 1 week before, we are able to predict that heat wave is likely. And of course, it may make small errors in terms of its intensity, etc., and duration, etc. But otherwise, the chance of getting a heat wave over a particular area is well predicted, at least 5 to 6 days before. And also, because of this only, many states government has now state action plan, heatwave state action plan. For example, Gujarat is a best example, Orissa, for example. So they all done heatwave action plan, which was initiated by NDMA. And so IMD is providing vital inputs to them, and they are able to do very well. And so I think all states should really. Only thing is, I see when the government knows about impending heat wave, ensuing heat wave is coming, what kind of action they should do? That there many times we don't do very well. We don't inform people properly, and people even after knowing that they don't take action properly. So the adaptation issues are there. So we need to really frame up some kind of policies for when heat wave comes. What are the actions to be taken strictly by government, public, NGOs, etc.
Thank you, sir. Sir, there are a lot of extreme events that we are experiencing these days, such as very hot days as well as very high precipitation days. Sir, is climate change the only reason for for witnessing such extreme events, or is there something else also?
Yeah, I think as I have been mentioning that there are two ways. One is it could be simple natural variability even without any human activities, and because of climate variability, so-called variability and natural variability, it can happen. It can happen. Yes. And so all these extreme events need not be attributed to natural climate change, human-induced climate change. It could be part of natural variability. So normally we have a tendency, any extreme event, we normally say, oh, it's all part of climate change. And best way, it's an easy way of doing it because you can wash off your hands saying that it's a climate change, so I'm not responsible, you do whatever you want. So, but which is not correct. So we need to really understand the so-called attribution studies we should make. Then, so any particular event cannot be attributed to climate change. It's very difficult to do unless you make a very detailed attribution studies.
Yes. So the next question refers to this only. So how can we differentiate between climate change and climate variability?
Well, that's a good question. And so climate variability, as I said that unless you have long-term data, it's very difficult to understand. And so if you past data will give you a kind of information about climate variability. Climate change normally we mean say like a systematic change in the global climate system, long-term trends, for example, is part of if you systematically analyze the trend and making an analysis, so then if you really see the trend, then that could be a part of climate change. But then here there could be a lot of variability within the system, within the trend itself. And so we have to really bifurcate climate variability and climate change. So many times we we don't understand the difference between these two. So we attribute anything which is a part of climate variability to climate change. So the differentiation is very important. You have to make the difference between climate change.
Yes, sir. Sir, could you also touch upon some of the steps that Indian government has taken to address the climate concerns?
Yeah, they have, for example, India is committed for going for alternate energy sources, for example, wind and solar energy by 2030 or so. Make a very big commitment as per the Paris Agreement we have made, India has made. Many countries have not made, for example, US has not made, China has not made, but India has made, and India is progressing very well. So my understanding is the Indian government is very much committed for mitigating climate change and contributing to the global initiative. And also, Ministry of Environment and Forest is doing a lot of work related to adaptation issues and mitigation issues of climate change and bringing out a lot of policies, etc. So we are doing our part. That's what. But as you know, that climate change, global climate change is cannot be done by one or two countries. It's a global issue. So all countries should really participate, especially countries who are emitting more and more fossil fuels. They should really come forward, and you should not tell an African country which they don't worry about any fossil fuel. They are worried about their one-time meal, food, and we should not blame them. We should blame few countries like US, China, Australia, European Union, who are all emitting more. They should contribute more. They should come out and they should have a little more kind of what you call commitment in mitigating climate change. That's not happening.
Very well said, sir. So Dr. Praveen Thakur was also having one question. Sir,
Yes.
Dr. Praveen? Yeah.
Yeah, sir, actually, this is more of a practical from the climate change projections. So recently we were doing some climate projection data from the downscale version we got from some of the resources. And this SSP scenario, even 2 and 3.6 scenarios, they were giving the very high temperature projections for Himalayan watersheds, going up to 8 degrees Celsius. So, and this previously we had this RCP 4.5, 8.5. So this gave very unusual kind of stream flow projections and
yeah. So what you have to do is you should not depend only one model. See, different models have its own way of projection. So depending upon the fidelity of the model, how good models are. Normally people do this kind of studies using multiple models, different kinds of models. They use more than kind of ensemble kind of thing. Then you can, instead of putting an actual value, talk in terms of probabilities, etc. So IPCC also has done the same thing. So they have considered all the models, and so you should not depend on only one model. That model will have serious biases. We don't know unless you test it for some other way. Whether the model is really good.
So actually, we have used CMIP6 models, 4-5 models. They were giving the
same CMIP6 model. There are different models, 40, 45 models are there. That's what my understanding. And all these models are not the same. So its fidelity is not same. It's not the same skill. The model don't have same kind of skill. Different model has its own problem. And so either you use the well-known climate models, like for example, GFDL models. There's all well-known models. GFDL model is a well-known model, and to some extent NGAR model, and so UK Met Office model. There are some well-known climate model.
And sir, one question related to this one only, this observational bias. So there are some bias corrections. So above 2000, we don't have the meteorological station. And how do we correct for the systematic bias? Because in the present time period, if I run 2006 to 2020, they don't match. So
if you don't have observations for Himalaya, I mean to say, IMD observation, we cannot really help. Maybe I don't know whether it's satellite observation can be used. I'm not sure. But you need observations to make corrections. You can use a regional analysis, for example, the model analysis called reanalysis. So regional reanalysis, for example, NCMR WF has brought out the regional analysis of 12-kilometer model resolution. So you can use that kind of first guess. You can use it for bias corrections. Otherwise, IMD observations, I'm not sure. You should use strictly IMD observation if they have. If you don't have, this reanalysis data will be better. NCMR data freely it is available. You can talk to them.
Yes. Thank you, sir. And
okay.
Sir, we can request EC members to switch on their video for a group photograph.
Yeah, maybe any other EC member, if you have any comment or question, we can take, and then otherwise we'll take a group photo and then we wrap up the session.
Yes. Dr. Adarsh, Meghaji. Yes. Yeah.
Okay.
Thank you very much, sir, for your very, very interesting talk. Although it was a little scary and a little depressing to really know the science and, there is no way out kind of a thing. But we hope that, all of us collectively take action now, although we are very, very late already. Thank you for your insights, sir.
Thank you, sir, from all the ISRS
EC
members.
Thank you, all of you. Thank you,
ISRS members, for sparing the time for this wonderful talk.
Thank you to you, sir, even sir, Dr. Shailesh Naikji, all the executive committee members and all ISRS colleagues for attending this very important function on World's Environment Day. Thank you, sir, and bye.
Thank you.
Thank you. Thank you, sir.